Chapter 7, Part 3, Mechanical Energy. Now, energy may be the most familiar and famous concept in science and in many other fields. However, it's still one of the most difficult concepts to understand, to define, and to picture. We observe the effects of energy when something is happening or when energy is being transferred from one place to another, or when energy is transformed from one form to another. In this chapter, we are interested in mechanical energy, a form of energy called mechanical energy. In fact, there are two forms of mechanical energy we will study. One is called kinetic energy and the other is called potential energy. So what is mechanical energy? Mechanical energy is a form of energy where objects acquire this energy due to position or to motion, or maybe both. Now, similar to work, energy is measured in units of joules. So work and energy have the same units. As we said before, there are two forms of mechanical energy. In this part, we will talk about potential energy. In the next part, we talk about kinetic energy. So what is potential energy? Now, an object may store energy because of its position or location. This energy, which is stored and held and is ready to be used for work, is called potential energy. And the reason for this potential energy is due to location or to position. The one potential energy we are interested in is called gravitational potential energy. Now, as you elevate or raise an object against Earth's gravity, you are doing work. This work will be stored in the object as gravitational potential energy. The potential energy, then, due to elevated position, is called gravitational potential energy. Example, water in an elevated reservoir has gravitational potential energy. In fact, any object that is elevated has gravitational potential energy. Now, the amount of gravitational potential energy is equal to the amount of work done against gravity to lift the object. So in this case, we can write an equation to calculate gravitational potential energy, saying that gravitational potential energy is equal to the weight, which is the force, times the height, the distance. So as you see, this equation really is calculating the work done against the gravity as we lift the object some height. So gravitational potential energy is equal to the weight times height. If you look at the picture in part A, now there is a rock, and this rock is raised above the ground a height of 2 meters. The weight of this rock is 100 Newton. So in this case, the amount of work done in lifting the object is 100 Newton multiplied by the height, which is 2 meters, and this gives us 200 joules of work. Now, this amount of work will be stored in the object as gravitational potential energy. If you look at part B, the amount of energy stored in the object as gravitational potential energy is the same as part A, because the height is the same and of course the weight is the same. So gravitational potential energy in part B is equal to amount of potential energy in part A. Similarly, in part C, the gravitational potential energy is exactly the same as in A and in B. Again, because the height is the same and of course the weight is the same. So gravitational potential energy only depends on the weight of the object and on the height to which it is lifted. General information. Now, hydroelectric power stations, they use gravitational potential energy of water. Water from a high reservoir flows through a long tunnel to an electric generator. So, gravitational potential energy of the water then is converted to electrical energy. Power stations in general, they buy electricity at night when there is much less demand and pump water from a lower reservoir back up to the upper reservoir. This process is called pumped storage. The pumped storage system helps to smooth out differences between energy demand and supply. Now we have a question here to think about. The question says, you lift a 100 Newton rock up for a height of 1 meter. So we know the weight of the rock, which is 100 Newton, and we know the height, which is 1 meter. So the first question is, how much work is done on the rock? Well, part A is very easy. To calculate the work, we already know the force and we know the height or the distance. So we multiply them together and the answer would be 100 joule. Part B is asking what power is expended if you lift the rock in a time of 2 seconds. Now, since we already know the work and we know the time, so power is equal to amount of work divided by time. 100 joules divided by 2 seconds, and this gives to 50 watt. Part C. What is the gravitational potential energy of the rock in the lifted position? Well, the answer, of course, if we measure potential energy from the ground, then the amount of potential energy will be exactly the same as the work we did, which is 100 joules.